Hello everybody, this is Mrs. Lindsay. Today we're going to talk about the triangle mid-segment theorem. Also could be called the triangle midline theorem. Okay, so let's take a look here. So you actually have three mid-segments of a triangle. What is a mid-segment? A mid-segment is, let me underline this, a segment that connects the midpoints of two sides. So everything in red here is a mid-segment in terms of the segments here. MN is a mid-segment because it connects the midpoint N of side AC and the midpoint M of AB. So this makes MN a midpoint, a mid-segment. Same thing with MP and PN. Now, traditionally, I would say it's probably drawn in this fashion where you're looking at it where AC is what we might call the bottom of the base, but again, it can be drawn anyway. So if I have a triangle, you know, that looks like this, and as long as I have connecting to the midpoint, this is also a mid-segment that I have here in red, and I would be referring to this down here as well. So let me just go ahead and put letters. So AB would be my mid-segment, and it has a relationship to CD. So this is what we call the triangle mid-segment theorem. Again, you might hear this sometimes be called midline. Same thing, midline, mid-segment. So if I have, again, D and E here are connected to the midpoints, that tells me two things. That tells me that DE is parallel to AC. And it also tells me the length of DE is half of AC. So again, if I'm referring to this document up here, AB would be parallel to CD, and AB would be half the length of CB. So if CB was 4, this would be 2. Okay? So again, you have three mid-segments of every triangle, and then you actually do have a mid-segment triangle that is formed if you connect all your mid-segments like you have up here. So mid-segment triangle is triangle MNP here because it connects all three of those mid-segments of a triangle. So let's do a few examples with this mid-segment theorem. Okay, so here we have DE is a mid-segment of triangle ABC. We want to find the length of AC. Well, since it tells us it is a mid-segment here, we know that E has to be the midpoint of AC, so this would be 4.8. Double that, and we get AC to be equal to 9.6. Okay. Let's go ahead and look at something I would call a coordinate proof here. That's really using our algebra, and it's just based on a coordinate plane here. So we have triangle, the blue triangle, RST. We want to show that MN is a mid-segment by showing it's parallel to RS, and that MN is half RS. So let's start with the first portion where it says show that it's parallel. Well, in order to prove that it's parallel, we got to find slope. Okay, so parallel lines, again, this is hopefully review for you, same slope. So in order to show same slope, since it's on the coordinate plane, we don't even need to use the slope formula. We literally count up 1, right 1, up 1, right 1. Same thing here for NM, up 1, right 1, up 1. So slope of RS equals the slope of MN, which equals 1. Therefore, MN is parallel to RS, right? So we did the first portion there. So now let's take a look at showing that MN is half of RS. Well, we can easily find these ordered pairs of M, N, R, and S. So let's go ahead and do that. So this would be 1, 2, 3, 2. And then RS would be 2, 5. And N would be 1, 0. And S would be -2, 1. So using the distance formula, we want to find the distance of RS, and we want to compare it to the distance of MN. Okay, so we'll start with RS. So we'll do -2 minus 2 squared plus 1 minus 5 squared. So 0, sorry, not 0, -4 squared plus -4 squared. So we're talking 16 plus 16, so square root of 32. And that right there tells us, again, if we do that, that is, this is equal to square root of 16 times the square root of 2, so that'd be 4 root 2. Okay. So now if we find the distance, using the distance formula of mn, that would be 1 minus 3 squared plus 0 minus 2 squared, which gives us -2 squared plus -2 squared. So 4 plus 4, so square root of 8. And that reduces into what? Root 4 times root 2. So that gives us 2 root 2. So you can see that mn is half of rs. So therefore mn times a half equals rs. Okay. So again, we're just using our algebra, and in this specific case, it's on a coordinate plane, so we're using our distance formula and various formulas that relate to your coordinates graph there. Okay. Our last problem is similar. Again, we're using a coordinate proof here, so same sort of idea, using our various theorems that we've done and formulas on the coordinate plane. But the only thing that's a little different here is if you look at the ordered pair B and you look at the ordered pair C, it doesn't have integers. It has variables in there, P, Q, and R. We still do the exact same thing, but our answers are not going to be nice, neat answers like 4 or 2 root 2. We're going to have P, we're going to have Q, we're going to have R in them. But again, we can still show that something's parallel and something is half the other by using slope formula, by using distance formula. So let's first start with showing FD is parallel to BC. Okay, so in order to do that, we actually have to find F, right? So in the beginning it says find the coordinates of F, which is the midpoint of OC. So this is going to be F. It's going to be the midpoint here. So halfway between 0 and 2p would be P. Halfway here would also be 0. 0 plus 0 divided by 2. That's all I'm doing for those formulas. Distant midpoint formula. Add together your x's, divide by 2. Add together your y's, divide by 2. So that gives us the coordinate for F. And then we want to show that FD, so let me go ahead and draw that in, is parallel to BC. So we want to show this. All right. So let's go ahead and we'll find the slopes of those. So we need to find the slope of DF, and we want to compare that to the slope of BC. Okay, so if we're doing DF first, now realize we don't have this ordered pair. Well, this is, if we're talking about midpoint, we're talking about showing parallel lines, this has to be the midpoint of OB. So again, using your midpoint formula, 0 plus 2q divided by 2 would give this an x value of q. Same idea, 0 plus 2r divided by 2, that would be r. So if we find the slope there, so change in y's over change in x gives you -r over p minus q. BC, same thing, change in y over change in x. Well, hopefully you see in this denominator when I'm simplifying that I can actually factor out a 2. So then that will cancel my 2's, leaves the negative, so it will actually be -r over p minus q, which again shows that FD is parallel to BC because same slopes. Okay? And just like we did before, we got to show that FD is half of BC. So we'll come over here, we'll use, now that we have all the coordinates here, again, we'll simply plug those in. So the distance of FD is going to be, again, subtract your x's, so it's going to be p minus q squared plus 0 minus r squared. And that doesn't really simplify a whole lot. P minus Q, we don't actually need to go through the process of foiling that out. We can just simply simplify the 0 minus r to negative r. We can leave it right there. If we need to come back and simplify it more, we absolutely can do that. But let's start finding the distance of BC and see if we need to go any further there. So BC in this case, so that's going to be 2P minus, I believe it's 2Q, yes, 2Q squared plus 0 minus, and I believe that was 2R squared. I'll double check that. Yes. Okay, so let's go ahead and simplify. So again, we have 2P minus 2Q quantity squared plus the quantity of negative 2R squared. All right, so let's take a look at this. We need this to be half of this. Well, hopefully you take a look at it and you're like, really looks like it is half already. What we can do here is we can actually factor these out. So let me show this extra step. So I could really do 2 squared and multiply that by the binomial P minus Q squared. And I could do the same thing here. I could make this 2 squared and leave this as negative R squared. So what happens is this is a common term that I can factor out. So that becomes the quantity 2 squared, and I'm going to factor it out of each of these. So then I would have left P minus Q quantity squared plus negative R quantity squared. And then I can now take the square root of that, which would make that 2 square root of what I have left over there, which is exactly half. So again, BC times a half. I'm not sure why I'm always writing it backwards compared to what the book does, but it doesn't matter which direction you go with that. So half of BC equals FD, because again, that would get rid of our 2 here. Okay, so that concludes our notes on the mid-segment theorem.